Okay. First of all, I want to thank everybody who joined last time and who's joining us today, and all of you are watching and sending emails with questions. It's really nice to know that I'm not speaking to myself, but someone actually hears and tries to understand. So this is super cool. So what are we going to do today? Last time we started speaking about AI and deep neural networks, how they work. We started looking at the various components. And today we are going to understand the concept of training. How is the training actually happening? And once we figure out the structure plus how the training is happening, we will explore some of the, I would say, traditional architectures for various computer vision tasks. And since when I first started giving this kind of a course, it was before the foundation model era, before transformers, before LLMs. So I didn't consider this as traditional. I just referred to it as architectures. But now we've been through a revolution in the last few years, and the world of AI itself has changed and revolutionized. So I will use this term as traditional AI to describe the exact architectures I'm going to speak about today. Okay, so let me share my screen. Boom, boom, boom. Yes, I'm going to share this one, and then we go to the other one. Okay, so just to go really like super fast on what we saw last time. So last time we actually, I think, understood that while in traditional computer vision or traditional analysis, we would look for features, and then the features extraction together with a classifier are combined into a single comprehensive framework, which is the neural network. So this is one thing. The second thing, we saw the structure of neural networks, so convolutions, and I got asked about convolutions, so I will repeat it in a minute. Then convolutions, feature maps, again convolutions, and then a fully connected layer where we are averaging and thresholding all of that to get some output. Now, I'm just reviewing, not going through the entire presentation. So we spoke about the basic, I would say, structure in deep neural networks, which is the perceptron, or the where you are making a decision. Just want to make sure that I'm still in the Zoom. One moment. It's a bit strange because I do not. Didn't I share my screen? I thought I did. Okay, let me see. So I'm going to, probably I forgot to share my screen. Okay, so now it's better. So we saw this structure where you have several inputs and they are weighted. We do some kind of weighted average, and then the big, I would say, the big sensation that it's not enough just to do this weighted average, but we really have to introduce some nonlinearity, which is basically the activation function. So only a weighted average which exceeds this activation function is transferred further in the neural network. So just moving further. So we talked about the fully connected network where all the inputs are taking part of the calculation. This is usually done in the very last layers of a deep neural network. And the convolutional part. So I want to repeat it one more time because I got some feedback that it was a little bit confusing for those of you who are not familiar with that. So when we speak about convolution, we are actually speaking about finding structures in images or in signals. And how do we do that? We create some kind of, let's say, a basic structure that we want to see how much of this basic structure, the filter, how much of it is actually in the image and where. So how do we do that? We move this filter and we put its center each time on top of another pixel of the image. So it slides over the image. And each time we are actually calculating the correlation. In image analysis, correlation and convolution are really, the same. They have the same meaning. And in mathematics, no. In image analysis, yes. So we try to find a correlation, and then the value that we get would tell us how much this information in the filter is correlated to a certain part of the image. And this means we are creating some kind of features extractor, because we ask ourselves how much of this feature that can be an edge, that can be smooth, that can be a circle, how much of this feature exists in a specific part of the image. Of course, these filters are not necessarily 3x3. They can have various sizes, but this is only for the sake of example. And then moving forwards, we also spoke about some sampling. So how do we shrink images, and why do we do that? We do that for two reasons. One, to make our computation faster, and the second is because we are doing a multi-scale analysis, which means that, like, if you are a pathologist and you are zooming out and you can see where the necrosis is, you can see where the tumor is, that's great. You don't need to go to the full resolution, you don't have to have like maximal magnification to see like the overall structure of your tissue. But when you want to find and count cells, then you need to zoom in. So it means that you can look at larger structures in lower resolution. Okay, but when you need to look at fine structures, you need higher resolution. So it's okay even if you are squeezing your image and you are decreasing its size, you are still able to see the larger structures. And this is exactly what this max pooling or subsampling is all about. Okay, so this is where we ended the last time, that we have the neural network. Fantastic. Now, I think that you all heard the term of training. We have to train the neural network before we can deploy it. So what is this training all about? And what training serves? So the training serves the aims to actually make the neural network do exactly what we expect from it. So we want to make sure that this neural network, this mathematical structure, is doing, let's say, most of the time, and to, let's say, a reasonable degree of certainty, we want to make sure that it's doing what we want. We want to be able to measure how well it performs. And we also wonder how can we make it, let's say that it doesn't work so well, how can we have a process where it can work better and better? And for all of these questions, the answer is training. And training is super important aspect. It usually requires a lot of data. It usually requires a lot of compute power. And so this is where I would say that the resources for deep learning and AI are needed, because if you need examples, then you need annotations. If you need to compute things again and again and again, then you need a cluster of GPUs to do that. So this is where the heavyweight of of deep learning actually lies. And and the issue of how to measure the error, then let's start from that because it's simpler. So we have our data, we have our neural network. So the data flows in the neural network and it provides some predicted output. The output can be, this is tumor. The output can be the boundary of the tumors, etc. So, but we have some prediction. And what we need to do, we need to somehow compare the prediction to the true or to the ground truth. And the ground truth, many times, we will see that now with foundation models, it changes. But for now, the ground truth is given by us. I mean, not me, but by you, by the pathologists, by the experts, because they provide the correct output, being it the limitation of cell, being it the I don't know, the type of tissue. The output can also come from another source. Let's say that we assume that there is H. pylori, and we have the PCR test. So, but we need to have some kind of a ground truth. And when we have the prediction of the neural network and the ground truth, we can compare them. Usually these would be values, either a single value or a vector of values, but we can see how different they are from each other. And this degree of difference, which is the error, is called the loss function. So we want to minimize the loss function. I mean, ideally, we want to make it 0, but life is not ideal. So at least we want to make it minimal. This is what we want to do. We want to make sure that if we train a neural network, then with time, the loss function is becoming smaller and smaller. And finally, what we would really like to achieve is to have the weights. The weights would be the parameters in the neural network. You remember when, let me take us a few slides before. So yeah, so each small perceptron, each small node in the neural network has a set of weights. And we want to make sure that these weights are the best so that we have the desirable result. So how do we get the set of these weights that minimize the error, that minimize the loss function? So what we can think about is some kind of a function that would be the error function. I would say the difference between what the neural network predicted and the ground truth. And this function can be a single value function. It can be 2-value function. It can be a vector of 60 values, but it's very difficult to draw, I would say, in 60 dimensions. So we stick to 2 dimensions. So what we see here would be a loss function. This means that here would be the minimum value, and probably somewhere here would be the minimum value of this loss function. And what this loss function depends on, it depends on the weights of the neural network. So try to imagine that the loss function is a function of all the parameters of the neural network. So you can imagine that this is really, you have not only X and Y, you have, I don't know, you may have millions of dimensions, and definitely this is something that we cannot draw. So let's stick to, let's say, only 2 parameters. And we are at the beginning, I don't know, we have some random parameters. So maybe our loss function would be here. So we want to create a trajectory. We want to create a process that would take us from here somehow to the minimum value. And it doesn't matter if we have X, Y, or X1, X2, X million, etc. Okay, it doesn't matter how many dimensions you have. The mathematics is the same. Also, loss functions can be very simple, but usually they are pretty complex. I mean, what does it mean? If you had a chance to experience with machine learning and deep neural network as users, then sometimes you get a result that doesn't make any sense. Okay, and you don't understand. I mean, this should work so well. Why doesn't it work as I want? Because maybe you see that this is here, for example, we have like the minimum, the actual minimum. But also over here, there is a small minimum value. It's a local value, but maybe in the process, I got stuck here. And I'm happy. I'm like in the minimum value for loss functions is like a place to relax, to sit in the sun and it's not too hot and you enjoy life. So I need someone to kick me off to kick me out of this cozy place that I found, and so that I will be forced to travel all the way to the actual global minimum value. And this is really a description of a very, I would say, widespread mathematical problem in optimization tasks, where you can get stuck in a local minima. So just that you know, sometimes we need to figure out how to get away or move away from local minima. So this is a problem. We will not handle it here. Just I think it's interesting to know that it exists. Okay, so how do we get to this minimum value? And what you see here is my cousin, who's a very, I would say, passionate bicycle rider. And here is aiming to travel close to the Dead Sea. What you see here is the Dead Sea. And since he's a very, very careful bicycle rider, then he usually takes, the routes which are almost horizontal. So it's very safe for him, but it's not very useful if you are a mathematician would like to get to a minimum value. Now, I really care about my cousin. I don't want to hurt him or to give him any suggestion to do things which are dangerous. But if I want to get to the Dead Sea as like promptly, I would take the direction which is steepest. It means that this is my loss function, okay? The valleys and the hills close to the Dead Sea. So I'm in the hill. I want to go to the minimum value. I want to go to the valley of the loss function. If I want to do it in the fastest way, I would take the route which is the steepest. And this is actually a mathematical paradigm, which is called steepest descent. It's really, as it sounds, we take the steepest descent. What we actually do, we measure, we say, okay, if I'm here and I go in this direction, how much lower will I get with the loss function? Not much, because this is almost a straight line. But if I take this direction, oh, now I'm talking. This will give me like a very nice decrease in the loss function. So not safe if you're a bicycle rider, but super, super fast if you are aiming to minimize loss functions. So going back to mathematics, what we say is that we take the gradient direction. The gradient would be the direction where our function changes most. Okay, and this is exactly what we want to do. So just try to imagine that for each and every parameter, because let's remember what are these hills and the valleys? These hills and valleys are actually the distribution of the function of our loss function as a function of the parameters of the neural network. So the question that we have to ask ourselves, how do I change the parameters of the neural network so that I will be traveling in the direction which is steepest and going down to the minimum value of the loss function? Also in one dimension, I think it's a bit clearer. At each and every point, if when it's one dimension, it's very easy. Either we go, if we are here, we can go to that direction, then we go up, or we can go to that direction, then we go down. So in one dimension, the question that we ask ourselves is, shall I go left or right in order to make my loss function smaller? So just try to extend it to million of parameters, which I have to admit it's a bit difficult, even for me. I mean, for me, even going to 3 dimensions is somewhat I would say confusing, but the principle, as I said, is the same. Okay, so now let's try to summarize. When I train the neural network, I have a set of parameters. I run my data in the neural network. I get some result, and then I can see where I stand with respect to the loss function. And I guess it's not zero. So I know that if I want to decrease it, then I have to take, for each and every parameter in the neural network, I have to change it in the direction of the gradient. So I need to calculate the gradient of the loss function with respect to each and every parameter of the neural network. And this is a lot of work. This is a lot of work. You don't do it analytically. So luckily for us, we have super intelligent people. Among them is Jeffrey Hinton from Canada, one of the godfathers of deep neural networks. And he phrased the coin of back propagation, which is a very, very important aspect, which is intensively being used in training of deep neural networks. So what's this back propagation all about? And again, I'm not, it's not a mathematical course. By the way, for those of you who are interested, I gave, but it's in Hebrew. Okay, well, if you know Hebrew, then I have a full mathematical course, and I think maybe I'll do an English version in the fall. Let's see. So here is our data. The data forward propagates. We have some error estimation. And then this error estimation is now propagating backwards in the neural network in a way that allows us to calculate in each and every node how you need to change the parameters of the neural network so that the loss function that we have calculated will be decreased. This is the concept, and this is the really how it is genius that we are doing it in an iterative way. So we change the parameters. Now we have another stream of data coming in. We have another loss function. Maybe it's a bit better than before, but we can again calculate the gradient and repeat it again and again and again until we reach a level of error that we can live in. That we can live with, okay? So, so this is like a more mathematical description of back propagation. I'm not going to go into that, but this is like some leftover from lecture 1. So how do we train neural network? We need the data. And I want to really say a few sentences about the data. So once upon a time, people thought that, okay, I'm going to give you like a lot of data. I'm going to collect so much data and scan and just take more and more and more data, and then I will drown you in the data. Not good, not good. Why is that? Because we need our data not to be huge. We need our data to be representative of the use cases that we want to handle. And the more a problem is difficult, the more data we would need to train the neural network, because it's like in life, you know, if you have a simple problem, probably you don't need to do a lot to solve it. If you have a more difficult problem, you need to put more efforts. And this concept of data and how much data do you need to train and how much data do you need to annotate, et cetera, this question or the answer to this question really changed dramatically once foundation models were introduced. Keep in mind this remark because we will go back to that in like 2 lessons. Once we have the data, and this is, by the way, also a place where the role of the expert is super important because only the expert knows whether the data that we have gathered for this training is representative. Then we are starting to forward propagate the data in the neural network, get to the loss function. Then are we happy with the loss function? Yes, no. If yes, our work is finished. If no, we need to back propagate, change the parameters, okay, adapt them and start all over again. Okay, so this is the training, and it really is like the basic of training of deep neural network. And when we finish that, we have the weights that minimizes the loss function. Okay, so this concludes our first session, and I already prepared for you lesson 2. So let's continue because this is like continuous. I don't see, let me check. I don't see any questions. So either that you understand everything perfectly or you don't want to ask anything. But also it's perfectly okay if you will send me emails and I'm very glad to answer emails. So if you don't like to ask questions here, please feel free to send me emails after the lesson. Okay. So now we know how a neural network is working and how it is trained. And once this was found, a lot of neural networks were developed, a lot of architectures of neural networks. And this was, I think, the main part of the work that was being done in the first decade, I would say, from 2012 to 2022, more or less. The aim, or maybe 2020 even. So the aim was to improve and improve and improve the architectures and find better and better architectures to achieve different tasks. Now, we are talking about pathology slides. So our summer school would be mainly focused on vision tasks, but we will speak about LLMs and we will speak about drug outcome prediction. But now I want to review with you the important tasks in computer vision. Now, this is my really the one and only my Bobby, who passed away 2 years ago, and this is Bobby as a puppy. I love to use this image. So the first task in computer vision would be to do classification. It means that I get an image which mainly contains the object that I'm interested in this case, a dog, and I want to develop a neural network which will tell me if this is a dog or not a dog. And you know, back in 2012 or 2014, when we started as a company to deal with the deep neural networks, then the toy problem that everybody was playing with was a cafe architecture or the cafe framework for differentiating between dogs and cats. So this is how we got started in deep neural networks. So when we talk about classification, we don't need to know whether dog is here or here or here. This would be done later on. This is like the simplest task. For example, let's take an example from pathology. So we have patches which contain cells, and they could be red blood cells or not. So what I want to do is I want to introduce each patch with cell to the neural network and to get as the output whether this is a red blood cell or not. So this is the meaning of classification. And the first architectures were really dealing with classification. And I think it's amazing when you review like the last 14 years, you see really how things evolved, and then there was like a singular point when we got transformers and LLMs. So just a quick reminder that, as I told you, the task of classification was very important to computer vision guys and girls, getting images and figuring out what is the class of the object in that image. And back in 2012, in a very nice location that I wasn't there, so I have no idea, but the AlexNet was first introduced and achieved the best of errors. So the AlexNet architecture was pretty simple. And I think that now we can, once we reviewed all the building blocks, we can dwell into it. So we have our input image. This input image is convolved, okay? It's going through the process of convolution with a lot of filters. And these filters, for each filter, you're actually getting a features map, which is, we will make it equal to the size of the original image, okay? But then we also, if we have, I don't know, if we have in that case 48 filters, then we get a box because each filter introduces one layer and we get a box. So the next convolution, after we do max pooling, the next convolution would be of other filters, and these filters will be like boxes. So we have a box of filters because we want to do the convolution on the entire box of features that we get. And so try to imagine that we do a lot of, features extraction, like massive features extraction in parallel. And eventually, all of this shrinks to a vector which has 2048 values. And this is, again, each layer here, remember, is composed of some kind of activation function. So not all the values survive. Some values are just zero. They're not interesting anymore. And at the end, we get a vector of 1,000 entries. Each entry represents another object. So let's say entry number 1 would be cars, entry number 2 would be planes, or entry number 3 would be dogs. And the value of each entry would give us the probability for the object to be of that category. So eventually, let's say that we have a dog, and the dog is the first category. So what would be the ground truth? The ground truth would be a vector, which is all zeros, but on the third place, you have 1, because in the ground truth, you are 100% sure that this is a dog. So let's say that we got a dog, and in the prediction, we didn't get everything 0 and only the third place is 1, because we didn't do the training yet. So what we do, we are calculating the differences between the probabilities, and we are summing them up for a number. And this number is the error, is the loss function. And if it's big, if it's not 0, because the ultimate best result would be a loss function of 0, then we are using the back propagation mechanism to decrease the loss function. How do we do that? By changing the parameters so that the loss function, remember, will be lower and lower in each and every iteration. Now, another way to look at the AlexNet would be in some kind of a diagram like this. So we have here all the operations, the number of filters, the size of the filters. So we see convolution 1, then max pooling, then we have 256 filters 5 by 5, again max pooling. And this means that we are creating coarser and coarser features. So you are like squeezing and squeezing and squeezing and squeezing the information until you get finally the result of vector of 1000. And I want to stop here for a moment, because in a way, when you look at that, it doesn't make sense that it works. How come that we are able to squeeze this information? And the truth is that because we are doing the training, we are punishing our parameters for being wrong, and we are giving them a prize for being right. How do we do that? With a big propagation mechanism. So, and this is why, and I think that you also probably heard about that, when you heard the term overfitting. Overfitting means that because we are here forcing our deep neural network to do what we ask it to do, then it means that if our data is not representative enough, it's too small, then it means that since this is like, this is the dictatorship neural networks, it's not democracy. I don't know, it's a combination. It means that I am forcing the neural network to do exactly what I want it to do, because I'm deciding what the ground truth is. So I'm deciding what's the error. So if your data is too small, then it means that you are really tweaking the parameters of the neural network to fit to the exact training examples that you gave. It means that it doesn't have the ability to generalize. If you want your neural network to generalize, it means that it has to see a lot of examples relative to the complexity of the problem and relative to the number of parameters. The larger your neural network is, the more examples you need. Okay. Another, so after what Alex, when AlexNet was presented in 2012, there was like a race towards better and better and better architectures to solve the classification problems. So VGG net was introduced in 2014. And what you see here, you see more layers in the deep neural network. So you see just AlexNet is, it's quite a humble neural network. So the more the merrier. So people started building like huge neural networks. At some point, they realized that having huge neural networks, at some point it starts, the performance starts decreasing, and they had to introduce some mathematical magic so that it would not happen. So there is the VGG. You see that the VGG is really much, much deeper. And when we talk about deep neural network, we actually talk about the number of layers. Okay, and nowadays in foundation models, in LLMs, in ChatGPT, etc., it's like as deep as the ocean. Okay, it's super, super deep. Okay, so we talked about classification. Another task in computer vision is that of semantic segmentation. Semantic segmentation means that we know about each and every pixel in our image, to which category it belongs. So now we are starting to combine classification together with localization. But take a look. We have here blue for cars. So we know that this is a car and this is a car, but when we do semantic segmentation, we are not able to distinguish between the two cars. Where does semantic segmentation, where is it useful in pathology? When we want, for example, to quantify the size of tissue. So we don't care if the tissue is here and there. We want to know the overall size of the tissue, and this is semantic segmentation. So, for example, this is wow, this is like an old version of our studio. Oh my God. Anyway, so this is a slide of bone marrow. And when we want to do semantic segmentation, it means that we want to have one category as one tissue and another category as the background or whatever. So eventually in semantic segmentation, each pixel has a label and the label equals the category. So how can we actually do that? So one way it would be, and this is Bobby now is a big dog with one of his friends. So one thing would be say the following. Well, I know how to do classification. Let's take from the image. Every time we'll take a piece of the image. So 1, 2, 3. And on each part of the image, let's make a decision about the class. And this is how we can determine the class of each and every pixel. So it is possible, but it's super not efficient. And when you are doing AI, you're not only thinking about how accurate you're doing, but also how efficient you do it. And I think that when we talk about energy crisis and the prices of training and the prices of hardware, these are critical questions because if these capabilities are not available for researchers or for companies, then because they are too expensive, then you simply can't use them. So another thing that you can do, which is more efficient, would be the following. I have a picture. In the picture, I have someone who's riding bicycle, and I want to segment it. So I want to segment person with bicycle, and all the other things are not of interest for me. So a fully convolutional network is a way to do semantic segmentation. And this is also, I think, when I look at it each and every time, I think I look at a miracle. I mean, it doesn't make sense that it works. Why? Because we are actually having here several convolutional layers. You see that the size of the original image is shrinking and shrinking and shrinking. And at some point, it's becoming larger and larger and larger until it goes back to the size of the original image. So we have image in, image out in the same size, but the image out would be the segmentation map. And again, the magic lies in the fact that we are comparing the prediction to the ground truth, and this loss function is advancing backwards in the neural network and tunes all the parameters. Now, this is a much more efficient because we don't go, like, we don't check each and every pixel and its environment separately. We already discussed yeah. So we already discussed downsampling, but you see that over here we have upsampling. So upsampling is also can be done very, very easily. If we want to take a 2x2 image and make it 4x4, then we can simply duplicate or pad with the zeros. So this is upsampling. And for medical applications, in AI, I like to say that the pace of how things really evolve in AI is so fast that you really need to run in order to stay in one place. But some good architectures really survive the agony of passing time, and one of them is UNet. UNet was developed in Germany, but I don't remember exactly where. I'm very lucky to know one of the authors of that paper. So UNet was designed for medical image segmentation. I know that it is widely used even today, although it was introduced, I think more than 8 years ago, which is like forever in AI. So how does UNet work? it's very similar to what we saw here. So the fully convolutional network, but it's a bit different. It's a bit different in the sense that, yes, indeed, we are providing the convolutional layers. We have the downsampling, continuing with the convolutional layers. At some point, all the information is shrunk into a vector, and then we have upsampling. Now, what's interesting here is that we are having these gray arrows. These gray arrows are some kind of sanity check of the neural network. It means that in each and every step, we are also transmitting the information that survived that layer. Why do we do that? We do that in order to have some kind of a way to make sure that the segmentation result will resemble our original image. We don't want to have a segmentation map for blood cells and get a segmentation map for dogs, okay? And we have to understand that, this is a bit of a philosophical thing, but, we talk about artificial intelligence. I think it's not a good name because it's artificial optimization. It's artificial structuring. It's eventually you are solving a mathematical optimization problem. I refuse to call it intelligence. So when you are using a mathematical framework for optimization, it means that if it's okay mathematically, it can take you anywhere. And this is why you need these constraints to make sure that you are more probable to arrive at a rightful, at a right conclusion. So U-Net really is super popular for semantic segmentation. And back, I don't know, I think it's definitely at least 6 or 7 years, all this work. So this is a U-Net-based application to do a segmentation in histopathology. And I can tell you that even today, you can get really superb results with U-Nets. So we saw the task of classification and also of semantic segmentation. But now we want to be more localized. We really want to track objects. Now, in order to do what we call object detection, we need to concentrate on two things. One would be to say where the object is, and the other thing is to say what's in there. So to have a bounding box and to say what's inside the bounding box. Now, this bridge is one of my favorite bridges in Rome. I bet it's pretty hot there right now. So, but it's also, I guess, super beautiful. So good for you if you're in Rome, but can get some nice ice cream and probably some, I don't know, crème de café. So the output of object detection would be the classification of the object and their bounding box. Again, and I think this is what I like about mathematics. In mathematics, you don't start with things which are complicated. You start with naive thinking. And naive thinking in this context would be to say, okay, I want to have bounding boxes. So let's create the huge number of bounding boxes in every size and orientation, etc., in every location in our image. Let's forget about orientation. Let's take all the possibilities as a function of location and size, and then I will extract the contents of each box, of each bounding box, and I will classify. Now, it's okay. It's possible. But again, it will be super, super, super time consuming. And a better idea. So this is not Bobby. This is not a dog that I had, but I'm really a huge fan of dogs. So a better idea would be, let's estimate where, in which bounding box you have a high probability for having objects, and let's concentrate only on these bounding boxes. Let's concentrate, and if I do this bounding box, I would say selection in a dense way, then I will see all the objects. Of course, I can always miss objects. Okay, this is again because once I'm making restrictions to make my life faster and more efficient, there may be a trade-off that I will miss some things. So, and Rosh Girshkik actually came with a series of super important methods for object detection at the family of RCNN, region-based convolutional neural network. And you see that it's 12 years old, still in use. And again, this means that it's a good thing. So what did he do? So you take the input image, you are designing some region proposal mechanism. So you are proposing the different regions to be analyzed. And then you have to warp each region so that it fits into the input parameters of your neural network. And, and the classification problem we know to solve. So we extract regions, each region we classify. That's it. When we know that in this region, there is a high probability for it to have a specific object, then we can label this region of interest, we can give it a classification, and our work is done. And it works beautifully. But again, we want things not only to work beautifully, we want them to work fast. So in the RCNN, the burden is that for each and every a region of interest, we need, to perform the full convolutional neural network and extract features and find the bounding box and etc. So this is a lot of work. So again, this Rosh Girshik came up 1 year later with a better idea, and naturally he called it fast RCNN. So the fast RCNN is handling the problem of the region proposals. And what he did here was to have one big neural network operating on the entire image. And, you can take any neural network that someone else developed, or if you want, you can develop one of your own. And this ConvNet is actually providing you the features for each and every pixel in the image. So now you extracted all the information for the entire image. So basically your region proposal is being done here. So you don't have for every region to duplicate the activity of the neural network. You do it once, you are using another neural network to do the image proposals, but you already have the features. So you saved a lot of work because you don't have to do it again and again and again. You only do it once. And this was really super cool, the fast RCNN. But it didn't stop here. There is a very, I would say, famous method, YOLO. You only look once. You also only live once, but this is not relevant to deep learning. But RCNN and fast RCNN, they don't look really at the entire image because eventually we have region proposals. With YOLO actually looks at the entire image. Nowadays, I think there is YOLO 12, It's really all the time improving and improving. YOLO is super great because it runs super fast, so it's very popular for edge devices. It may not provide as good results as RCNN. But YOLO is super famous, a lot in a lot of use. And what you actually do, you apply a single neural network on the entire image. And this neural network is actually giving you two predictions. One prediction are bounding boxes, which have high probability for having a object, and also for a specific grid, we are predicting the class that resides in that area. So what we have to do, we have to combine the prediction of the bounding box and the prediction of the class that overlaps with the bounding box. And we do it one time with when we look at the entire image only once. So this also gives pretty good results, especially in terms of speed. Okay. The last task, and this is good because we are almost at the top of the hour. The last task, which is very important in pathology, is that of instance segmentation. What you see here are beta amyloid plaques, and they are all of the same type, but we want not only to count the number, because in order to count the number, I could have like bounding box around each and every plaque, but let's say that I really want to have the area, the exact area of each and every plaque. This is, by the way, part of work that we've done a couple of years with Professor Jan Svanke from the University of Oslo. So how do you do that? How do you also get the exact boundary and not only the bounding box? And this is, by the way, this is called instance segmentation. You want to segment the instance and not only put the bounding box. So one popular method for that is mask RCNN. And this is also a pretty old method, and you can see because this was first developed when we had COVID. Remember, we had COVID like a few years back. So mask RCNN is again relying on the work of Roche Girschkik, and it employs a detector. So in the same way that we have for mask RCNN, but also predicts the boundary of the object. So basically what we have is some, again, features extractor with regions proposal. So this is pretty much the same as the RCNN or the fast RCNN framework, but then it has two paths. One path would be to have an object detection, so to have the class, and the other path would be to predict the mask. So to do prediction of the mask and have the exact boundary. Okay, so I really reviewed, I would say, fast, and I hope intuitively, and a really high level, the architectures that serve some of the important problems in computer vision, and this actually would finish our interaction with classical deep learning. It's not that that I've said everything you have to say about it, but I want us to jump and do this jump in the beginning of this decade and figure out what are these foundation models, what are these transformers, what are these LLMs, because nowadays what we have is, besides the set of traditional AI tools, not to talk about traditional computer vision, of course. We have an amazing set of new tools that is making its way super strong in pathology. So, guys and girls, I do thank you for keeping up with this presentation. I see that most of you, the majority has survived it, which makes me super happy. Again, if you have any questions, you are super welcome to send it over to me to Chen, CAGN, at DeePathology.ai. I will do my best to answer. If I don't know, I'll simply tell you that I don't know. And tomorrow we will send an email over to everybody with links to the recording. So stay tuned. Looking forward to meeting you next week. And I wish you all a cool day wherever you are. Thank you, guys. Bye-bye.